So I'm going to use tonight to explain centripetal acceleration and the basics of some rotational motion. So we're going to take a look at an object moving in a circular motion. We can write the position in terms of Cartesian coordinates. X equals r cos theta and y equals r sine theta. So if we just think about this for a second, I like to do a little example. If theta is 0, our x position is at r on the Cartesian plane, and our y sine of 0 is just 0, so y is 0, and we know we're at the right spot here. So if I want to use calculus, I can get the x and y components of the velocity are, so if we're just going to be looking at it rotating around, the derivative is going to be the rate of change of theta, how fast things are changing in the rotational way, and the derivative of cos is negative sine theta, and I can do the same thing for the y velocity. Derivative of sine theta is cos theta, of course. So I'm just going to say the rate of change d theta by dt. This is going to be equal to omega, which is going to be a constant. So this is only assuming that the rotation around the circle is following some constant. It's not suddenly accelerating, going faster. So I'm just going to rewrite my Vx. It's going to be r omega, negative r omega sine theta, and my Vy r omega cos theta. So from this, if we take a look when theta is equal to 0, subbing in, our x velocity is now 0, and our y velocity is r omega. And notice it'll be in the positive direction, noting that our velocity is now at a 90-degree angle. And because we know from the trig identity that cos theta and sine theta are offset by 90 degrees, at any point along the circle, we can assume that the velocity, or we can solve for the velocity being at a tangent. And in fact, if we took a look at the case of theta equal to 90 degrees, if we sub this in, the sine of 90 is 1, and we notice we get Vx equals negative Rw, because it's now pointing in the negative direction. We can also show that the magnitude of the velocity at any point is going to be the square root of Vx squared plus Vy squared. This is just from the definition. And if we sub in our values here, we're going to get negative Rw sine theta squared, so the r will be squared and the negative will go away. And the same thing to our y. Oh, that's a cos. And we can factor out the r omega, and we're just left with sine squared theta plus cos squared theta, which we know is equal to 1. So our final magnitude for the velocity is just the square root of r squared omega squared, or r omega. So now I'm also going to look at acceleration. So I can take the derivative of the velocity with respect to time. In the x direction, I'm going to get sine becomes cos, so negative r omega d theta by dt, the rate of change as we're going around the circle comes out again, and a cosine theta. And we know that this is defined as omega, so we'll have negative r omega squared cos theta, and we'll have a similar argument for the y component. We will have r omega d theta by dt, and the derivative of cos is negative sine. I'll put that negative out front. And we're left with negative r, this is another omega squared sine theta. This is our x acceleration and our y acceleration. So just taking another look, at first when theta was 0 we were at the position x equal to r. Our velocity was totally in the y direction. Now when theta equals 0, our acceleration, if we sub it in, ax, cos of 0 is 1, we're going to get negative r omega squared. So in the x direction, it's going negative, and in the y direction, if we sub in theta to be 0, we're just going to get sine of 0 is 0. So we've proven that, in fact, for all theta, because they're offset by 90, when the velocity is traveling in the x direction, the x component is now going to be always at 90 degrees from that trig identity of the sine and cosine being offset by 90 degrees. And we can also have a similar argument for the magnitude of A at any point. We'll get something that looks like r squared omega to the 4th, and we'll still have that now a cos squared theta plus sine squared theta, again being 1. So our acceleration at any point is just going to be equal to r, magnitude of acceleration, is r omega squared. So here, omega is in units of radians per second, and omega is equal to 2 pi, so the rotational value, actually at the center, there's no radius to it, divided by the period. And so we can see now, since acceleration, no matter what direction we're in, if we're going to look at one more direction, so this is for theta equal to 90, subbing this in, cosine of 90 is 0, there's no x component for the acceleration, sine of 90 is 1, it's going to be negative rw, so pointing down here. Of course we know at any time it's to the center. So this relates to our centripetal force, or our force is equal to ma. When we're going in a circle, acceleration is always to the middle. So this creates a centripetal force. And we can write this centripetal force as m, and we know that this is going to be our omega squared. So I'm just going to continue on and show how we can find the tangential velocity vt at any point. So we know that omega is 2 pi over t, And if we also looked at rotating in a circle, we know the going all the way around would be 2 pi times the radius. That's going to equal the distance around. And if we divide that by the time to go around, which is known as the period of rotation, we would get a tangential velocity. And we know since omega is 2 pi over t, we sub this in here, omega r is vt, where omega is equal to vt over r. And going back to our formula for centripetal force, Fc was equal to mr omega squared. So if we sub this omega in, mr vt squared over r squared, we'll get an r canceling out. And there we have a formula for centripetal acceleration, or centripetal force. And the acceleration would just be divided by the mass, so we get a vt squared over r. It's also worth noting from the position going to rewrite x and y. We can get, by subbing in a value for omega in radians per second, we can get the point we are along the circle. I just wanted to show that. So if we assume t equals 1, omega would be equal to 2 pi. And then for t equal to 1, for t equal to 0, 1, 2, we would always be back at this point. 1, 2, 3, so you're always just putting a pi in. The same will of course hold true to calculate your velocity if you wanted to replace theta with omega t. And the acceleration as well.